Hey there, science explorers, ready to dive into the fascinating world of coordination complexes? Ever wondered why some solutions with metal ions have such vibrant colors? Or how we predict the magnetic properties of these compounds? The answer lies in understanding how electrons behave around metal ions, and that's where crystal field theory comes in. It's like a secret code that unlocks the mysteries of coordination complexes, which are essential players in many chemical and biological processes. So, if you're ready to ace your chemistry exams and impress your friends with your newfound knowledge, put on your thinking caps and join me on this exciting adventure. We'll break down complex concepts into bite-sized pieces, work through practice problems together, and arm you with the tools you need to conquer crystal field theory. Let's get started. At the core of crystal field theory lies the concept of crystal field splitting energy, denoted by the symbol delta naught. Imagine a lone metal ion, happy and content with its electrons buzzing around in their usual orbitals. Now picture a bunch of molecules or ions called ligands approaching this metal ion, eager to form bonds. These ligands, like tiny magnets, create an electric field around the metal ion. This field disrupts the peace and harmony of the metal ion's d orbitals, causing them to split into groups with different energy levels. The energy difference between these split d orbitals is what we call delta naught. This value depends on several factors, including the type of metal ion, the nature of the ligands, and the geometry of the complex formed. Understanding delta naught is crucial because it directly influences a complex's properties, such as its color, magnetism, and reactivity. Now let's talk about electron configurations in coordination complexes. Remember those split d orbitals? Electrons prefer to occupy these orbitals in a way that minimizes the overall energy of the complex. This is where the concepts of high-spin and low-spin complexes come into play. Think of it like a game of electron Tetris. In high-spin complexes, electrons prioritize occupying all the available d orbitals with the same spin before pairing up. They're like rebellious teenagers who want their own space. On the other hand, in low-spin complexes, electrons prioritize pairing up in the lower energy d orbitals before occupying the higher energy ones. They're like well-behaved guests who prefer to share rooms. Whether a complex adopts a high-spin or low-spin configuration depends on the balance between two opposing forces: the pairing energy, which is the energy required to pair up two electrons in the same orbital, and the crystal field splitting energy. If delta naught is smaller than the pairing energy, the complex will be high spin, and if delta naught is larger than the pairing energy, the complex will be low spin. Section 4. Crystal field stabilization, energy, quantifying stability. Now that we understand how electrons arrange themselves in coordination complexes, let's quantify the stability gained from these arrangements. This is where crystal field stabilization energy, or CFSE, comes in. CFSE is like a measure of how happy the electrons are in their new split d orbitals compared to their original unsplit state. To calculate CFSE, we assign energy values to the split d orbitals. In an octahedral complex, for example, the three lower energy orbitals are assigned an energy of minus 0.4 delta zero, while the two higher energy orbitals are assigned an energy of plus 0.6 delta zero. We then sum the energies of all the electrons in the d orbitals, taking into account their occupancy and spin. The difference between the total energy of the electrons in the split d orbitals and their energy in the unsplit state gives us the CFSE. CFSE is always a negative value, indicating that the complex is more stable than the free metal ion. A more negative CFSE value corresponds to a more stable complex. This stability influences various properties of the complex, including its reactivity and thermodynamic behavior. Section 5. The colorful world of transition metal complexes. One of the most striking features of transition metal complexes is their vibrant colors. But have you ever wondered what gives these complexes their dazzling hues? The answer lies in the interaction between light and the electrons in the split d orbitals. When light shines on a transition metal complex, electrons in the lower energy d orbitals can absorb photons of specific energies and jump to higher energy d orbitals. The energy difference between these orbitals corresponds to a specific wavelength of light. The color we perceive is the complementary color of the absorbed light. For example, if a complex absorbs light in the red region of the spectrum, it will appear green. The magnitude of delta zero plays a crucial role in determining the color of a complex. A larger delta zero generally leads to the absorption of higher energy light, resulting in complexes that appear yellow, orange, or red. Conversely, a smaller delta zero leads to the absorption of lower energy light, resulting in complexes that appear blue, green, or violet.